Lecture 1. Quantum Computing Fundamentals. Qubits, Superposition, and Entanglement. Quantum computing represents a new paradigm of information processing that leverages the laws of quantum mechanics to perform computations beyond the reach of classical computers. Classical versus quantum bits. In a classical computer, information is stored in bits that take a value of either 0 or 1. Quantum computers instead use quantum bits or qubits, which can exist as U1 or a superposition of both 0 and 1 simultaneously. Superposition means a qubit is described by a complex linear combination of the basis states 0 and 1, endowing it with richer states than a classical bit. While it's common to say a qubit can be 0 and 1 at the same time, this is a simplification. More precisely, the qubit state is a probability amplitude distribution over 0 and 1 that doesn't have a direct analog in everyday experience. The power of superposition is that a set of qubits can encode an exponentially large amount of information in their joint quantum state, compared to the same number of classical bits. Entanglement. Beyond superposition, quantum computing's other magic ingredient is entanglement. Entanglement is a quantum correlation between qubits such that their states become deeply interconnected. Once two qubits are entangled, measuring or affecting one instantly influences the state of the other, within the confines of quantum statistics, no matter how far apart they are. Entangled qubits lose their individual identity and must be described as a combined system. Importantly, the amount of information needed to describe an entangled multi-qubit state grows exponentially with the number of qubits. This implies that entangled qubits can represent extremely complex probability distributions that would be infeasible for classical systems to simulate directly. In practical terms, entanglement allows a quantum computer to process an enormous number of possible outcomes in parallel, which is the key to its potential computational advantage. Quantum versus classical computational power. Because of superposition and entanglement, even a relatively small quantum register can outperform classical supercomputers on certain tasks. For example, with on the order of 50-60 high-quality qubits, a quantum computer could execute specific algorithms in minutes that would take the world's most powerful classical supercomputer billions of years. This dramatic speedup arises in problems like factoring large numbers, simulating quantum physics, chemistry, or combinatorial optimization, where classical computing time explodes exponentially with problem size. Quantum algorithms, like Shor's algorithm for factoring or Grover's for search, harness the parallelism of superposition and the correlations of entanglement to explore many possible solutions simultaneously, rather than one by one, as a classical computer would. It is important to note that quantum computers do not simply try all solutions at once, in a naive sense. The process is subtler, involving interference of quantum amplitudes to amplify correct answers and cancel out incorrect ones. Designing algorithms to effectively use this property is a non-trivial task in quantum information theory. Nonetheless, quantum hardware provides a computational resource fundamentally different from classical logic, and for certain problems this resource yields provable speedups. Qubits in physical systems. Qubits are realized in various physical forms, e.g. the spin of an electron, the polarization of a photon, the energy states of an atom or ion, or superconducting circuits. Regardless of implementation, all qubits obey the same quantum mechanical principles. What distinguishes implementations are practical attributes like coherence time, how long the qubit can maintain its quantum state, gate fidelity, how accurately we can manipulate the qubit, and scalability, how many qubits can be controlled together. These factors determine the viability of a quantum computing platform. Leading approaches today include superconducting qubits, employed by IBM, Google, and others, and trapped ion qubits, employed by IonQ, Quantinuum, etc., among others like neutral atoms, silicon spin qubits, and photonic qubits. In summary, this lecture has introduced the foundational concepts of quantum computing. Qubits that leverage superposition to encode more information than binary bits, entanglement that links qubits inextricably and provides exponential complexity, and the promise of quantum algorithms to solve certain problems exponentially faster than classical algorithms. In upcoming lectures, we will delve deeper into how these principles are harnessed in practice and the challenges in building a large-scale quantum computer. Lecture 2. Trapped ion qubits. High fidelity and all-to-all connectivity. Having covered the general ideas of qubits, we now focus on a specific technology that is central to Merope Quantum's context: trapped ion quantum computers. Trapped ions are one of the most promising qubit implementations due to their excellent coherence and high-fidelity operations. In a trapped ion system, each qubit is an individual atomic ion, such as ytterbium or barium, that is electrically charged and held in place by electromagnetic fields in a vacuum chamber. Typically, ions are confined using electric fields in devices called Paul traps or surface electrode traps. The qubit's logical states are two internal energy levels of the ion, for example, two hyperfine spin states of the atom. Laser beams are used to perform operations. By shining precisely tuned lasers on the ions, we can rotate a single ion's qubit state, single qubit gates, or induce coupling between two ions, two-qubit entangling gates. In essence, lasers provide the push that causes ions to interact via their mutual Coulomb force and become entangled. High-fidelity operations. One of the major advantages of trapped ion qubits is the demonstrated gate fidelity. Experiments have repeatedly shown that both single-qubit and two-qubit gate operations in ion traps can surpass 99% fidelity, i.e., less than 1% error per gate. In fact, trapped ion systems hold records for some of the highest fidelity quantum logic gates. For example, IonQ, a leading ion trap company, recently reported achieving greater than 99.9% two-qubit gate fidelity using barium ions, exceeding the 3 nines threshold. Such high native fidelity is extremely valuable because every quantum algorithm requires many gate operations, and errors can accumulate. As IonQ's engineering SVP noted, crossing 99.9% is a critical milestone where the need for error correction overhead is significantly reduced. In practical terms, an error rate of 0.1% or lower per gate means quantum computations can be much longer deeper before noise overwhelms the result, compared to gates with 1% error. High fidelity is a cornerstone for scalability, as we'll discuss in later lectures on error correction. Long coherence. Times. Trapped ion qubits also enjoy long coherence times, meaning the ions can maintain their quantum state, superposition, for relatively long durations before decohering. Because the ions are identical atoms and are electromagnetically isolated in ultra-high vacuum, they interact minimally with environment noise. Coherence times in trapped ion systems are often measured in seconds or even minutes, which is orders of magnitude longer than superconducting qubits that tend to decohere in microseconds to milliseconds under similar conditions. Longer coherence gives a larger time window to perform computations and even implement error correction cycles before the qubits lose information. This intrinsic stability of ions comes from using natural atoms, which are all identical and have stable energy levels, rather than manufactured circuits which might have material imperfections. All-to-all connectivity. Another strength of trapped ion processors is their connectivity. Because all the ions in a trap are charged and coupled through collective motion, in an ideal ion trap any qubit can in principle interact with any other qubit directly. This is often referred to as global or all-to-all connectivity. In IonQ systems, for example, any pair of ions can be entangled via a single two-qubit gate operation without needing intermediate swaps. This is a stark contrast to many other platforms, like superconducting qubits on a chip, where qubits usually can only interact with their nearest neighbors, requiring additional operations to move information around and entangle distant qubits. All-to-all connectivity simplifies quantum circuit implementation and can reduce the total number of gates needed for algorithms. It also means we can design error-correcting code, layouts, or algorithm mappings with more flexibility, not being limited by a fixed geometry of connections. Trapped ion scaling limits. Thus far, Trapped ion experiments have entangled on the order of tens of ions in a single trap. As of late 2023, the largest fully controlled entangled state is 32 ions. IonQ's latest commercial system, IonQ Fort, is reported to have 35-plus qubits available, and another ion trap venture, Innsbruck U of Maryland, demonstrated a 50-qubit simulation of magnetism with ions. These achievements underline that ion traps can indeed host dozens of high-quality qubits. However, scaling to hundreds or thousands of ions in one trap faces practical difficulties. More ions require more complex electrode structures and laser addressing, and motional modes become harder to control as the chain length grows. There are physical limits like electric field stability and mode crowding that make extremely large single traps challenging. For instance, trapping 50 ions in one chain is feasible, but trapping 1,000 in one chain would be far more complex due to accumulated charge and stability issues. To address this, researchers have developed two main strategies, which will be focal points for Merope Quantum's approach. 1. The QCCD, Quantum Charge Coupled Device Architecture, where ions are shuttled between multiple trapping zones on a chip, dividing qubits into smaller groups that can interact as needed. And 2. Modular ion traps connected by photonic links, where multiple separate traps, each with a manageable number of ions, are entangled with one another via photons. Both strategies aim for scalability by networking smaller quantum registers into a larger one. The next lecture will delve into this scalability challenge and how modular architectures come into play. In summary, trapped ion qubits provide an attractive foundation for scalable quantum computing thanks to their high gate fidelity, 99%, long coherence times, seconds, and full connectivity. These properties make them a leading platform and directly motivate Merope Quantum's focus on overcoming the remaining bottleneck, scaling up via connecting multiple ion trap modules. We will next explore why scaling is non-trivial even with such excellent individual qubits, and how the scalability crisis manifests. Lecture 3. The Quantum Scalability Challenge. From single trap to modular systems. Even with qubits as pristine as trapped ions, building a large-scale quantum computer is a tremendous challenge. Researchers estimate that solving classically intractable problems, like factoring large RSA integers or simulating complex molecules, may require millions of physical qubits with error correction. This lecture examines the scalability crisis in quantum computing, why one cannot simply keep adding more qubits to a single device indefinitely, and why modular, distributed quantum architectures are needed. Merope Quantum specifically targets this problem of scaling quantum computers beyond the confines of a single trap or cryostat. Why we need millions of qubits. To appreciate scale, consider that a recent analysis showed factoring a 2048-bit RSA number, a task impossible for classical computers, might require on the order of 20 million noisy physical qubits if using current error correction schemes. Similarly, quantum algorithms for chemistry or optimization that outperform classical methods typically demand thousands to millions of logical operations. Each logical qubit, error-corrected, effectively noise-free qubit, might be encoded in hundreds or thousands of physical qubits depending on error rates. Thus, a full-scale fault-tolerant quantum computer likely needs 10 or 6, 10 or 7 physical qubits working in concert. This is astronomically higher than the 50-100 qubits present in today's best experimental devices. Bridging this gap is the central challenge of quantum engineering. Monolithic scaling versus modular scaling. One approach is to scale monolithically, e.g. trap more ions in a single trap or fabricate a larger superconducting chip with more qubits. However, monolithic scaling runs into serious engineering and physics roadblocks. In trapped ion systems, as mentioned, a single trap can only hold a limited number of ions before control becomes untenable. More lasers and control electrodes are needed, and disturbances, vibrations, electric field inhomogeneities grow with system size. In superconducting qubits, wiring and refrigeration become limiting. Each additional qubit needs control lines and contributes heat load. Today's largest superconducting chips have a few hundred qubits, and pushing beyond thousands on one chip is daunting. Given these limits, the field is turning to modular scaling. The idea is analogous to classical computing clusters or multi-core processors. Build multiple smaller quantum processors, modules, and connect them together to function as one larger computer. Each module might contain, say, 50 or 100 qubits that interact internally, and modules communicate with each other via some networking method. This could be done via matter, e.g., physically moving qubits between modules, in ion traps. Shuttling ions between different zones or traps on a chip is one approach. Or it could be done via light, using photons to entangle qubits in different modules, essentially a quantum network linking quantum chips. The photonic interconnect vision, the most promising route for long-range, centimeter-to-meter scale and beyond, connections is using photons, particles of light, as carriers of quantum information between modules. This is conceptually similar to how classical computers in different locations are networked by optical fibers, except here we need to maintain quantum coherence. In a typical scheme for ion traps, or neutral atoms, each module has certain qubits designated as communication qubits. When we want to entangle module A with module B, we excite a communication qubit in each module to emit a photon, often via an optical cavity or a laser pulse. These two photons, each entangled with the state of their originating qubit, are then interfered on a beam splitter and measured. If the measurement has the right signature, it projects the two distant qubits into an entangled pair. This technique is sometimes called entanglement swapping or a heralded bell swap. The result is a bell pair shared between module A and B. This bell pair can then be used as a resource for performing gates between qubits in different modules, for example, via quantum teleportation protocols. Key metrics: fidelity and rate. For such photonic interconnects to be useful, two metrics are crucial: the fidelity of the entangled bell pair generated, and the rate, how many entangled pairs can be produced per second. Fidelity is essentially the quality of the entanglement. It needs to be very high, ideally 0.99 or 0.99, so that using the entangled link for computation doesn't introduce too many errors. Rate is important because quantum error correction and complex algorithms will consume many entangled link operations. A slow link becomes a performance bottleneck. Unfortunately, current experimental implementations of remote entanglement have faced limitations on both fronts. Photonic links tend to suffer loss and noise. Photons can be lost in fiber, or background light can cause false detections, etc., which degrades fidelity. As distance between modules increases, loss typically increases exponentially in fiber. Even at short distances, within the same lab, achieving near-unit fidelity entanglement is hard. As a benchmark, current state-of-the-art photonic links between ion trap modules achieve on the order of less than 90% fidelity for entanglement, meaning a 10% error rate on interconnect operations. This is significantly worse than the nominal 99% fidelity of local gates inside one trap, highlighting a major gap. Additionally, the rate of entanglement is often in the few hertz to a few tens of hertz range in early experiments. Each attempt might succeed with low probability, needing many retries. The industry recognizes targets to make modular quantum computing viable. One commonly cited goal is 10,000 plus bell pairs per second at 99% fidelity between modules. Achieving $10K entangled pairs per second with RS 1% error or less would likely be sufficient to perform distributed quantum error correction and link modules without overwhelming the system with errors. For comparison, academic proposals have started approaching these numbers in theory. A recent research paper on neutral atom modules projected that with advanced cavity designs, one could generate remote bell pairs at rates approaching the megahertz, million per second range with fidelity around 99.9%. Extremely encouraging if realized. But as of now, experimental realizations are far slower and noisier than these aspirational targets. Merope Quantum's focus, the bottleneck. We now see clearly where the critical bottleneck lies, connecting multiple quantum modules. Inside a single module, like a single ion trap, we can perform high-fidelity operations with error rates below 1%. But between modules, current photonic interconnects might have error rates an order of magnitude higher, 10%, and low success rates. Such errors are above the threshold for error correction. Lecture 5 will cover thresholds, meaning a 10% error link would render a large distributed system unworkable unless improved. This is precisely the scalability crisis highlighted by Merope Quantum. As they note, even if each rack of an ion trap quantum system is internally 99.99% reliable, connecting racks by optical links is the Achilles heel, losing coherence and fidelity with distance and environmental interference. Without solving this, building a quantum computer beyond one rack, say hundreds of qubits, stalls out. IonQ's roadmap offers a real-world example. IonQ aims to network modular rack-mounted quantum computers in data centers by 2023 plus. They anticipate that achieving broad quantum advantage will require moving to error-corrected systems around 2025 and beyond, which implies linking many modules. IonQ has invested in technology to address this. For instance, their acquisition of a photonic interconnect startup, Lightspeed LightSynQ, and a quantum memory firm, indicating that scaling via networking is a key part of their strategy. By 2026, IonQ expects 256 connected qubits and long-term targets millions of qubits by combining modules. All these plans hinge on boosting interconnect fidelity and rates. To summarize this lecture, scaling up quantum computers necessitates moving from single-module to multi-module architectures. This introduces new challenges because intermodule entanglement is currently slow and error-prone compared to operations within one module. The goal and the focus of Merope Quantum is to push those interconnect performance metrics into a regime that supports fault-tolerant, large-scale systems. For example, approaching 10,000 bell pairs per second at sound 99% fidelity. In the next lecture, we will examine in more detail how photonic entanglement links work and what causes the loss of fidelity, as understanding that will guide us to strategies for improvement. Photonic interconnects and distributed quantum networks. This lecture dives deeper into photonic interconnects, the technology enabling quantum entanglement between separate quantum computing modules, or nodes. We will discuss how these links operate, the sources of error and loss, and recent advancements. By understanding the mechanics, we can appreciate why Merope Quantum emphasizes real-time tuning and monitoring for such links. How photonic entanglement links work. At its core, a photonic interconnect uses photons, particles of light, to carry quantum information between distant qubits. One common method is the heralded entanglement protocol using interference and detection, briefly mentioned in the previous lecture. Here's a more concrete scenario in the context of trapped ions. Suppose we have ion A in module 1 and ion B in module 2 that we want to entangle. Each ion has an excited state that can emit a photon when the ion transitions to a lower energy state. We prepare each ion in a superposition that is correlated with whether or not it will emit a photon, for example, using a laser pulse. The emitted photons, one from ion A and one from ion B, are directed into optical fibers and meet at a common beam, splitter, or interferometer. At the beam splitter, the two photons become indistinguishable and are subsequently detected by photon detectors. Due to the quantum interference effect, certain detector click patterns, e.g., one detector firing and not the other, indicate that the two ions have been projected into an entangled state, even though we never directly interacted the ions. This detection is heralding the entanglement. We know entanglement succeeded because of the pattern of photon measurement outcomes. In practice, the above process is probabilistic. Many attempts might be needed before an entangled pair is successfully created. The probability of success depends on factors like the efficiency of photon collection from the ions, transmission loss in fibers, and detector efficiency. Using optical cavities around ions can greatly boost photon collection rates, by funneling emission into a certain mode. Even so, losses are significant. Fiber cables, for example, have attenuation on the order of 0.2 dB per kilometer for telecom fibers, but even a few meters of imperfect coupling can lose a chunk of photons. Moreover, if multiple attempts are needed, achieving a high entanglement generation rate requires minimizing the time per attempt, which is often limited by things like the ion's fluorescence lifetime or how fast detectors can reset. Sources of infidelity. The fidelity of the entangled bell pair produced by the above method can be degraded by several mechanisms. First, there's the obvious issue of photon loss. If one photon is lost and the other is detected, the attempt fails. No entanglement created. Usually, a herald event requires coincident detection of two photons. Any loss typically means no herald, and you try again. Loss, per se, doesn't directly reduce fidelity of successful trials. It just lowers the rate. But other errors do. Dark counts in detectors, a detector clicks even with no photon due to noise, can falsely herald an event that didn't actually entangle the ions, leading to a wrong state. Mode mismatch in the interferometer. If the two photons are not identical in spectrum phase, the interference isn't perfect, and the resulting 2-qubit state is not a pure Bell state, but a mixture. Timing jitter can similarly blur the interference. Environmental factors like vibration or temperature drift can detune the interferometer or optical path lengths, causing phase errors. All these contribute to less than ideal fidelity in the entangled link. Crucially, a photonic link's fidelity can decrease with distance because longer fibers mean more opportunity for decoherence and loss. Even within a single lab, distances of a few meters, keeping photons indistinguishable and in phase is non-trivial. Across a data center, tens of meters, or between buildings, it gets harder. Researchers often employ active stabilization, e.g., sending classical laser pulses through the fiber to measure and correct phase drift, or temperature controlling the fiber paths. State-of-the-art, achieving high-rate, high-fidelity links is an active area of research often overlapping with quantum communication and quantum network R&D. As noted, a key metric pair is bell pairs per second and fidelity. Let's consider some numbers from recent progress. In 2021, University of Innsbruck showed entanglement between two ions in separate traps, with fidelity around 94% and rate on the order of 50-100 entangled pairs per second at a few meters distance. In 2023, Oxford researchers achieved entanglement between two superconducting qubit modules using microwave to optical conversion, albeit at very low rates, demonstrating principle of modular linking across different tech. A 2224 proposal for neutral atoms we encountered projected 0.999 fidelity and near M8's rates using a carefully designed optical cavity system containing many atoms. In that scheme, by having multiple atoms in one module ready to attempt entanglement in parallel, the amortized entanglement attempt rate skyrockets, and a novel cavity design suppresses errors to reach 99.9% fidelity. This theoretical work highlights that there are paths to reach the desired regime, thousands plus of high-fidelity entanglements per second, with clever engineering. Meanwhile, companies like IonQ and Quantinuum are certainly working on their proprietary approaches. IonQ's acquisition of Oxford Ionics and LightSynQ, photonic link specialists, suggests that integrating those technologies is expected to yield multi-rack systems in the coming few years. Quantum networks versus local links. It's worth noting that the effort to link quantum modules in a computer is closely related to the idea of a quantum internet, entangling qubits over long distances, kilometers. However, for a modular quantum computer, the distance might be just within one room or one facility, which relaxes some constraints. We can have fibers or free space links that are shorter and perhaps more controllable than a global network. Still, many techniques are shared. For instance, quantum repeaters are devices proposed to extend entanglement over long distances by chaining shorter links together with intermediate memory and entanglement swapping. In a large modular computer, if you have many modules, you could imagine a network topology where not every module is directly connected to every other, but entanglement can be routed through intermediate modules, like a network graph. In that case, having some form of repeater functionality or entanglement swapping between modules will be needed to distribute entanglement where needed in the computation. The design of such networks, and the underlying protocols, is an emerging discipline. Standards bodies, like the IETF, are even considering metrics and architectures for quantum networks, where metrics like bell pairs per second and fidelity are analogous to bandwidth and packet loss in classical networks. Merope Quantum's perspective: photonic interconnects present dynamic problems. Unlike static qubits in a single device, these links involve flying qubits, photons, and lots of analog components, fibers, beam splitters, detectors, that can fluctuate. Merope Quantum's strategy, as we will see, is to incorporate real-time telemetry and control to adapt to these fluctuations. For example, if a link's loss starts increasing or an alignment drifts, the system should notice immediately via sensors and error rates and adjust, maybe by retuning a phase shifter or increasing laser power, etc., on the fly. The goal is to maintain coherence across distributed quantum networks despite environmental noise. This could involve predictive noise modeling, e.g., anticipating when a vibration from a nearby machine will disturb the link, and preemptive compensation. These ideas will be explored in Lecture 7 on real-time control. To conclude, photonic links are the connective tissue of a scalable quantum computer, but they currently are the weakest link in terms of fidelity. Achieving high fidelity, high-rate entanglement distribution is an active research frontier. Advances in optical engineering, like better cavities, more efficient detectors, quantum memories to buffer qubits during connection, and smart control systems, feedback loops to stabilize channels, are expected to push performance towards the fault-tolerant thresholds needed. Merope Quantum's focus on adaptive, real-time management is precisely aimed at squeezing the maximum performance out of these delicate photonic interconnects. Decoherence and fidelity. The need for quantum error. Correction. We have repeatedly touched on fidelity, the accuracy of quantum operations in links, and how finite fidelity limits the size of computations we can run. In this lecture, we focus on the twin issues of decoherence and noise in quantum systems, and how they motivate the use of quantum error correction, QEC. This forms the theoretical foundation for why Merope Quantum's push for 99% plus fidelity is so critical. Decoherence and noise. Sources. Decoherence is the process by which a qubit loses its uniquely quantum behavior, superposition phase coherence, due to interactions with its environment. It's essentially the qubit becoming entangled with uncontrolled environmental degrees of freedom, which, from the perspective of our computing, looks like the qubit has randomly collapsed or changed. All physical qubits decohere eventually. The goal is to delay this as long as possible, long coherence time, and/or perform computations faster than decoherence. Sources of decoherence include stray electromagnetic fields causing phase rotations, e.g., magnetic field fluctuations for spin qubits, thermal excitations causing spontaneous state flips, coupling to vibration, for trapped ions, motional heating of the trap can cause qubit errors, or leakage out of the defined qubit states. In photonic systems, loss is analogous to decoherence. Loss of the photon, warp-bars, loss of information. Aside from idle decoherence, gate operations themselves are imperfect. Control pulses can over-rotate or under-rotate a qubit. Pulses can off-resonantly affect other qubits, etc. These introduce gate errors. Measurement of qubits can also be noisy, e.g., a detector might report the wrong outcome occasionally. In summary, at each step of a quantum computation, storing a qubit, applying a gate, transmitting a qubit, measuring a qubit, there is some probability of error. Quantum error. Correction. Threshold. The central insight of quantum computing theory is that as long as error rates are below a certain threshold, we can use redundancy and correction circuits to suppress errors arbitrarily well. This is analogous to classical error correction, like parity bits, CRC codes, etc. But quantum error correction is more complex due to the no-cloning theorem, We cannot directly copy unknown quantum states, and the need to correct both bit flip and phase flip errors. Nonetheless, many QEC codes exist: Shor code, Steen code, surface code, etc. A commonly cited rule of thumb is that gate and memory error rates around 1%, 99% fidelity, are roughly the threshold for some of the simplest codes. In fact, John Martinis, who led Google's quantum hardware team, stated that 99% fidelity is the ballpark threshold for error correction. Getting error rates to below 1% was a long-time goal to even start implementing useful QEC. Different codes have different thresholds. For instance, the surface code, a popular 2D lattice QEC code, has a threshold around 0.75 to 1% for depolarizing errors. Some more advanced codes, like certain LDPC codes, might tolerate a few percent, and others require below 0.1% if noise is biased. The implication is stark. If your physical qubits and operations are worse than our 1% error, adding more qubits will not help, because attempts at error correction will introduce more errors than they remove. You would be in the regime where complexity only adds noise, and the whole system's effective error might blow up. This is why demonstrating 99% fidelity in 2-qubit gates was a watershed moment. It means we can cross from the noisy intermediate scale quantum (NISQ) era towards the fault-tolerant era. Notably, various platforms have now achieved this. As mentioned, trapped ions have, and superconducting qubits have seen 2-qubit fidelities in the 99.5% range in research as well. Single-qubit gates are often even higher, 99.99% or better in many cases, and readout error is improving. However, 99% is enough is a bit oversimplified. In practice, we want error rates well below the threshold to reduce the overhead of QEC. For example, with 0.1% errors, 99.9% fidelity, the number of physical qubits needed per logical qubit might be in the low hundreds. With 1% errors, 99% fidelity, it could be thousands. One study by IBM estimated that around 99.999% fidelity might be needed to make the overhead manageable for certain algorithms. This is why IonQ pushing to 99.9% fidelity is so important. Each additional 9 of fidelity dramatically improves the outlook for building a feasible quantum computer. Each additional 9 means an order of magnitude less errors. Quantum error correction. Basics. How does QEC work? The core idea is to encode one logical qubit across multiple physical qubits in such a way that if a small number of them error, the errors can be detected and corrected without measuring the logical information. For example, the surface code, one of the most studied codes for 2D architectures, uses a grid of physical qubits where entanglement and multi-qubit measurement operations, parity checks, are done on subsets, usually via ancillary qubits, to glean information about errors. One does not measure the qubit's logical state directly. Instead, one measures syndrome bits that tell you where an error occurred. By periodically doing these syndrome measurements, one can locate and fix errors, usually via a classical algorithm, since the syndrome gives a parity check matrix, much like a classical code, and then applying corrective quantum gates. Error correction itself is an involved process that requires additional operations, which themselves can error. This overhead is why having as high fidelity as possible is crucial. If your error correction cycle introduces too many new errors, it undermines the benefit. As a concrete number, Google's 2023 experiment with a surface code demonstrated a logical error rate lower than the physical error rate for the first time, a milestone for QEC, by encoding a logical qubit in 49 physical qubits with physical gate error, thus 0.4%, and achieving logical error, thus 0.1%, showing error reduction. This shows error correction can work, but at significant resource cost. Distributed error correction. Now consider error correction in a distributed multi-module quantum computer, the kind Merope Quantum envisions. Not only do we have to correct errors within each module, but we must consider errors on the links between modules. If we treat the whole multi-module setup as one big quantum computer, we'd likely run a large QEC code over it. Imagine a surface code patch that spans qubits in different modules. Measuring a stabilizer, parity, that involves qubits in two different traps would require an entanglement link between traps. If that link has 10% error, it's far above threshold and the code will fail. Therefore, for distributed QEC to work, the intermodule link fidelity must also meet the threshold condition. This reinforces the industry target of 999% link fidelity. If we can get the network error rates to almost 1% or less, we can incorporate them into the QEC process. One approach to handle slightly lower fidelity links is to use quantum repeaters or entanglement purification protocols. For instance, one can generate multiple low-fidelity bell pairs and then perform a purification, entanglement distillation, protocol that consumes several noisy pairs to output a fewer number of higher fidelity pairs. This improves fidelity at the cost of rate. However, such protocols themselves require additional qubits and gates, quantum memory to hold pairs, etc. And ultimately, they too rely on being above a threshold. Importance of real-time error. Monitoring. Until we reach fully error-corrected operation, today's quantum processors operate in a mode of frequent calibration and mitigation. Techniques like dynamic error suppression, e.g., dynamical decoupling pulses to refocus qubit phases, and error mitigation, post-processing results to reduce error effects, are used. Merope Quantum's philosophy of real-time telemetry fits here. By monitoring error rates continuously, one can imagine applying adaptive error mitigation. But in the long term, the holy grail is to incorporate automated error correction at the physical level, which means a combination of high-fidelity hardware and fast classical controllers to do syndrome processing and feedback. In summary, decoherence and noise inevitably plague quantum operations, but quantum error correction offers a path forward if our error rates are low enough. Achieving 99% fidelity across the board, including any interconnects, is the entry ticket to scaling up via fault tolerance. This is why improvements in fidelity, like IonQ's 90 quantum error, correction and fault tolerance, from theory to practice. Building on the motivation from Lecture 5, we now delve into how quantum error correction, QEC, is implemented and what it takes to achieve fault-tolerant quantum computing in practice. We'll discuss specific QEC architectures relevant to platforms like trapped ions, and the immense engineering complexity involved in orchestrating error correction across potentially thousands or millions of physical qubits. Logical qubits and overhead. A logical qubit is an abstract, error-protected qubit represented by the state of many physical qubits. The ratio of physical qubits per logical qubit can be very high. For instance, a surface code, logical qubit with distance d dollars, which can correct up to two batteries d1, $2 errors, uses about d2 physical qubits. To correct, say, up to 2 errors, d5, one might need 25 qubits for one logical qubit, and that code would have a logical error rate that might still be on the order of 0.1% or more per operation if physical error is under 1%. To get logical error rates exponentially small, e.g., 10 $9 per operation, which might be needed for a long algorithm, d dollars might need to be 15 or 25 or higher, implying hundreds of qubits per logical qubit. And that is per logical qubit. A full algorithm might require hundreds of logical qubits. It becomes clear why estimates run into millions of physical qubits for significant tasks. This overhead can be somewhat improved by better codes. LDPC quantum codes, low-density parity check, are a newer class of codes that generalize the surface code concept and potentially allow fewer qubits per logical at the cost of more complex decoding. Interestingly, the Merope quantum architecture mentions LDPC syndrome extraction in the context of ion shuttling, suggesting they foresee using advanced QEC codes. Surface code itself is actually an LDPC code in a sense, but there are even more efficient ones under study. Researchers are actively trying to design codes that have higher thresholds or require less overhead, but all roads still demand high-fidelity hardware. Real-time feedback. In QEC, fault tolerance isn't just about encoding. It requires a tight interplay between the quantum hardware and classical control system. In a QEC cycle, one typically performs a round of quantum gates that entangle data qubits with ancilla, measurement qubits, to extract error syndromes, then measures the ancillas. The measurement outcomes, classical bits, are fed into a classical decoder algorithm which computes where errors likely occurred, and then based on that, decides on recovery operations, which could be doing nothing if no error, or applying a corrective quantum gate like an X dollars or Z dollars on a specific qubit. This entire loop must happen faster than the errors accumulate too much. In many proposals, the decoding can be done in parallel with subsequent QEC rounds, pipelined, as long as the decoder latency is within certain bounds. For solid-state systems, superconductors, decoders implemented on classical FPGAs or even GPU-CPUs have been developed. In trapped ion systems, one advantage is the longer coherence time, which could allow slightly more slack in decoding time. However, trapped ion gates are slower, microseconds to hundreds of microseconds per gate versus nanoseconds for superconducting gates. So the QEC cycle itself is slower. Balancing that, ions can wait longer before decohering. Either way, real-time processing of syndrome data is essential. This is an area where software-hardware co-design is critical. Merope Quantum's platform likely envisions feeding telemetry, like syndrome outcomes, into a classical processor that could even use machine learning or pre-computed lookup tables to quickly decide on corrections. Trapped ion-specific, QEC, the QCCD architecture. In a single monolithic ion trap, error correction can be done by designating some ions as data qubits and others as ancilla qubits within the same trap. Indeed, small QEC codes, like a 7-qubit Steen code or a 15-qubit Bacon-Shore, have been demonstrated in single traps. However, as codes grow, one runs into the issue that every qubit pair might need to interact. If all ions are in one chain, in principle that's fine, all-to-all connectivity, but gates between distant ions in the chain might be slower or less reliable. Moreover, the laser pulses for many gates might interfere if many are done simultaneously. The QCCD quantum CCD approach proposed by Kielpinski, Monroe, Wineland in 2002 suggests dividing ions into separate zones for storage and interaction, and physically shuttling ions as needed to perform gates, then separating them again. For example, one could have an interaction region where a small number of ions are brought together to enact a gate, then those ions move apart. This way, one can arrange a schedule of operations where not all qubits are interacting in one big crystal at once, reducing crosstalk. In the context of QEC, imagine we have a surface code. One may shuttle specific ions, qubits, into a zone to interact with an ancilla for a parity check, then shuttle them back. Meanwhile, other shuttling operations happen in parallel in other zones. Ion shuttling operations include moving ions linearly, splitting a group of ions into two groups, merging two groups, and even swapping ion positions. All these have to be precisely controlled with time-varying voltages on trap electrodes. They also carry some error risk, e.g., heating up the ion's motion slightly each shuttle. The Merope quantum architecture explicitly references an ion shuttle scheduler that uses linear programming to optimize these movements and avoid collisions. Collision-free scheduling means planning the routes of ions so that two ions don't end up in the same trap zone or crash into each other when shuttling through a junction. It's very analogous to routing traffic. They also mention LDPC codes, Surface Code Syndrome Extraction Scheduling, confirming that their scheduler is intended for managing the sequences of operations needed to measure the many parity checks of something like a surface code using ions. The scheduler likely needs to ensure all necessary syndrome measurements occur within a certain time frame, the error correction cycle time, without conflicts, and while minimizing total operation time. One of the impressive points listed is throughput, 1,000 plus parallel shuttle operations. That suggests their software aims to handle thousands of ion movements in parallel, which might correspond to a very large ion trap chip with many zones all operating simultaneously. Achieving that experimentally would be cutting edge. It implies a highly parallel trap architecture, perhaps something like a 2D grid of traps. Fault-tolerant gates. Aside from correcting errors, one eventually needs to perform logical operations, gates, on the encoded qubits. Fault tolerance demands that even these operations be done in a way that doesn't spread errors uncontrollably. In many QEC codes, certain operations, like a logical C0 or logical Hadamard, can be done via a series of physical operations that touch many qubits but are arranged so that if a few physical errors occur, they don't cause a logical error unless corrected by the code. This often involves more complex circuits or techniques like magic state distillation for T-gates, an advanced topic where one prepares special states to perform non-Clifford operations on logical qubits. The details are beyond our scope, but one takeaway is that achieving universal fault-tolerant computation further multiplies the overhead, e.g. magic state factories to supply distilled ancillas for T-gates may consume a large fraction of qubits in some architectures. For Merope Quantum's interest, ensuring the intermodule links are also used in a fault-tolerant way is key. There is research on fault-tolerant entangling of modules. For example, one might treat a noisy bell link as an error to be corrected and incorporate it into the syndrome measurements, like have multiple link attempts and compare them. Another idea is a teleportation-based gate. To do a logical gate between logical qubit A in Module 1 and logical qubit B in Module 2, you teleport A into Module 2 using an entangled link and then do a gate locally, which can be fault-tolerant if the teleportation uses purified high-fidelity bell pairs. All these schemes are complex, but they highlight that how we integrate modules matters for fault tolerance. Current status. No quantum computer today has reached the true fault-tolerant regime, where logical errors are well below physical errors and one can run arbitrary long circuits reliably. However, the first steps have been taken. Distance 3 and distance 5 codes showing some error suppression, small logical qubits surviving longer than any physical qubit, etc. The roadmap for the next few years for most companies is to demonstrate a logical qubit that has significantly lower error than any physical ones and then scale that up. IonQ, for instance, has mentioned pursuing low overhead error correction experimentally. Given ION's high fidelity, it's plausible they can get there with fewer qubits than others. From an academic perspective, achieving a useful logical qubit might require, say, on the order of 100 physical ions and significant classical processing. Merope Quantum's platform seems to be preparing the software and control infrastructure to handle such a situation, with real-time telemetry, so they can detect any anomaly quickly, Bayesian tracking to always estimate the current error rates, and optimized scheduling to use resources efficiently. Essentially, it's providing an operating system for a fault-tolerant quantum computer, dealing with all the timing, control, and error management tasks in the background. In conclusion, quantum error correction is our strategy to overcome decoherence and noise, but it demands extreme precision, lots of qubits, and fast control systems. It is the bridge to fault tolerance, where the quantum computer's logical operations become reliable no matter how large the algorithm, as long as the noise per operation is below threshold. Real-time monitoring and control of quantum hardware. As we move from theory to implementation, one of the key challenges is keeping a complex quantum computer operating at peak performance in real time. This lecture discusses the role of real-time monitoring, telemetry, and feedback control in a quantum computing platform, an area where Merope Quantum has invested with its high-speed control center. When running a quantum system with many components, lasers, traps, detectors, etc., things can drift or fluctuate on timescales ranging from microseconds to hours. Without active control, these drifts would quickly degrade fidelity. Hence, a quantum computing control center, as Merope Quantum puts it, is necessary to constantly supervise and adjust the system. Classical analogy. In classical computers and data centers, we have monitoring of temperatures, clock rates, error logs, network traffic, etc., often with automated responses, like adjusting a fan speed or load balancing traffic. In a quantum computer, we need an analogous concept, but with even tighter timing and unique signals. For example, one might monitor the frequency of a laser driving an ion transition. If the laser drifts off resonance by a tiny fraction, gate fidelity will drop. Or monitor the vacuum pressure in an ion trap chamber. A spike could indicate an event that might cause ion loss or increased collision-induced decoherence. Many such parameters exist. RF trap voltages, magnetic fields, cryostat temperatures for superconducting systems, photon detector, dark count rates, etc. Telemetry. Systems. Merope Quantum's architecture describes a Rust telemetry daemon responsible for ingesting a large stream of data with ultra-low latency. It cites 10,000 events per second, sustained throughput with sub-millisecond processing latency. What are these events? They could be results of qubit measurements, signals from sensors, like a stabilized laser's error signal, hardware status pings, or quantum circuit execution logs, e.g., a gate done, a qubit state reported. Sub-millisecond responsiveness indicates the system can react on the order of microseconds to milliseconds. In trapped ion terms, a single gate might be a few microseconds long, so if something goes wrong, say a sudden noise burst is detected, in principle a feedback could be applied before the next operation. One concrete example of real-time control is active feedback to qubits. Some quantum experiments have demonstrated feedback loops. Measure one qubit and use the result to apply a conditional operation on another qubit, all within microseconds. This requires fast classical logic and delivery of a control pulse. In a modular system, similarly, one might measure a link fidelity in real time and adjust a parameter. For instance, if a photon detector is registering more background counts than expected, the control system could momentarily increase a discrimination threshold or trigger a recalibration of that detector's baseline. Adaptive calibration. A significant portion of real-time control is actually rapid calibration routines. Quantum hardware typically requires frequent calibration of e.g. laser pulse lengths, qubit frequencies, crosstalk offsets. Instead of manual calibrations once a day, an advanced system might continuously calibrate in the background. For example, between algorithm runs, it might send diagnostic pulses to qubits to measure any drift in gate performance, and then tweak the pulse amplitude accordingly. Merope Quantum's mention of auto-tuning that adapts to photonic channel degradation in microseconds is a prime example. If a photonic link is getting worse due to some noise, the system can respond almost instantly, perhaps by increasing error correction on that link or adjusting the temporal mode of photons. Sensors and data. To do this, many sensors are deployed. For photonic links, sensors could include single photon counters, monitoring background rates, interferometer phase monitors, e.g. using a continuous laser to track phase drift, and even environmental sensors, temperature, vibration via accelerometers on optical tables. For qubits, sensors are the qubits themselves, via calibration sequences, and any classical readout apparatus associated with them, like RF pickups that measure trap electrode impedance, etc. The telemetry system must aggregate all these streams. We see in Merope specs mention of 1,000+ concurrent connections, likely to various devices or sensor channels, using async I/O. Each connection might be a data source publishing at, say, kHz rates or higher. The platform uses techniques like zero-copy data handling to achieve the required throughput. Real-time dashboards and alerts. On top of raw data, the control center would likely have a real-time dashboard, showing, for instance, current qubit fidelities, vacuum level, laser lock status, etc. If something strays out of bounds, automated alerts or shutdown procedures might kick in to protect the experiment, just like how in a particle accelerator, if a magnet current goes out of spec, the system dumps the beam to avoid damage. Maintaining distributed coherence. One specific phrase, distributed coherence management, in Merope's description deserves attention. Managing coherence across multiple racks means ensuring that all modules share a consistent reference frame for quantum phases. If two modules' clocks, or laser phases, drift relative to each other, remote entanglement can acquire phase errors. So one might distribute a master clock signal, e.g., a stabilized optical frequency comb, to all modules. Then, telemetry would monitor any phase offsets and correct them. If Module A's oscillator is 5 Hz off relative to Module B, after 1 second they'd be $5 times 2 for P radians out of phase. The control can detect this and apply a phase correction to the measurement outcomes or on the fly to the next operations. Essentially, the whole multi-module system needs a phase synchronization, like a giant interferometer. This might involve frequent exchange of reference photons or using GPS-like synchronization techniques within the data center. Latency considerations. A challenging aspect is that any feedback loop has latency. If it's too slow, it can't fix fast errors. Merope Quantum lists an error correction latency 2.3 ms achieved in their solution. That is impressively low. 2.3 microseconds from detection to correction. If true, that's on the order of 1 or 2 ion gate times, which means their control system can apply fixes almost immediately. Compare that to typical classical systems. A 2.3 ms latency suggests an FPGA-level control rather than a high-level software, or at least highly optimized code paths perhaps on real-time OS. Possibly, they offload critical feedback to FPGAs, or even custom ASICs, while higher-level decisions, like Bayesian estimation to refine parameters, run in software slightly more slowly. Bayesian monitors. Tying into lecture. 8. A Bayesian fidelity tracker can be running continuously to give an up-to-date estimate of how well the system is doing. For real-time use, instead of running a full 1,000-sample MCMC for each update, which might take seconds, one might use a running filter, e.g., a Kalman filter or particle filter, to update fidelity estimates on the fly. The Bayesian model could flag statistically significant drifts, e.g., Qubit 5's error rate has increased from 0.5% to 1% over the last minute with high confidence. Take action. That action could be to pause computations on that qubit and recalibrate it. Integration with user operations. The control system must also interface with the user's quantum program. If a user submits a quantum circuit to run, the system might break it into schedules for each module, orchestrate the photonic link usage, etc. If mid-run a problem is detected, say a link fails to produce entanglement for too long or a qubit drops out, the system might decide to retry certain operations or even dynamically reroute the algorithm, maybe use a different qubit as a spare. This is speculative, as current quantum programming usually doesn't incorporate dynamic rerouting, but future robust systems might have such fault-tolerant protocols where the controller can adjust the execution based on live feedback, a concept akin to quantum operating systems. In summary, real-time monitoring and control is the central nervous system of a large quantum computer. It continuously senses the state of the hardware and applies minute adjustments to keep the machine aligned and stable. Without it, drift and noise would accumulate, undermining the high fidelities we worked so hard to achieve. Merope Quantum's emphasis on telemetry, microsecond-scale adaptation, and predictive adjustment underscores that a successful quantum computing platform is as much a feat of classical control engineering as it is of quantum physics. The next lecture will focus more on the algorithms that such a control system can use, in particular, how machine learning and optimization, like Bayesian methods and ZX calculus, are employed to fine-tune and streamline the quantum operations.